Albert Einstein is considered one of the greatest scientists who ever lived. He has entered the collective imagination as the epitome of genius, a very selected club of individuals, including only a handful of others, who are almost universally recognized as having changed our view of the world. This is the fascinating story of what happened that one time when Einstein got it wrong. In the early morning of December 31st, 1930, Albert Einstein and his wife Elsa arrived in San Diego, California for a much-awaited 2-month-long visit to the California Institute of Technology in Pasadena and the Mount Wilson Observatory, at the time the prime observatory in the world. The Einsteins had left Berlin on the evening of November the 30th, then sailed from Antwerp on December the 3rd aboard the steamer SS Belgenland, where they occupied 3 luxurious staterooms permanently filled with fresh flowers, courtesy of their American hosts. Einstein didn't appreciate the attention though, as he found the accommodation excessive and pretentious. They reached California after a stop in New York, where photographers and journalists lunged out at him like hungry wolves, as befitted a scientific personality who achieved rock star status before there even were rock stars. When Einstein arrived in Pasadena, the hype around his visit had reached such an intensity that he was besieged by the press, photographers, autograph seekers, and crackpots of every description. Crowds of small boys gathered wherever he went. Shopkeepers stocked special merchandise worthy of the planet's smartest man. The predictions of Einstein's theory of general relativity, which he published in 1915, had been spectacularly confirmed by observations of the apparent position of stars around the Sun during a total solar eclipse in 1919. On that occasion, newspapers around the world hailed the discovery in almost mystical terms. The New York Times blared, "Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations." The special cable reporting from the Royal Astronomical Society meeting in London, where astronomer Arthur Eddington had presented the results of the eclipse expedition he had led, quotes the Royal Society president and Nobel Prize winner J.J. Thomson. He is saying that the difference between Newton and Einstein's theory of gravity can only be expressed in scientific terms, strictly scientific terms. It is useless to endeavor to detail them for the man in the street. In the same cable, the solar astronomer William James Lockyer, the son of Sir Norman Lockyer, the discoverer of helium, was more reassuring, if perhaps involuntarily self-aggrandizing. He said, "The discoveries, while very important, do not, however, affect anything on this earth. They do not personally concern ordinary human beings. Only astronomers are affected." Perhaps no astronomer was keener to meet the great theoretical physicist than Edwin Hubble, whom we see pictured here. Hubble had made himself a name as one of the greatest extragalactic astronomers of the time, aided in this by his having access to the largest telescope in the world, the 100-inch Hooker telescope at Mount Wilson, and being helped by an exceptionally skilled assistant, Milton Humason, who rose from being a janitor in the observatory to become Hubble's indispensable right hand at the telescope. In 1923, Hubble had settled once and for all the question of whether the Andromeda Galaxy was part of our own galaxy, the Milky Way, as some insisted, or a galaxy in itself. Hubble established that Andromeda was over a million light years away from the Milky Way, and therefore could not possibly be a part of our own galaxy. It was the first other galaxy discovered as such in the universe. A discovery that I discuss in greater detail in my Gresham lecture, Understanding the Universe with AI. By 1929, Hubble, with the help of Humason, had amassed measurements of the distance of several dozen galaxies, together with observations of their spectra. A spectrum, in the physicist's jargon, is the breaking up of light from a source into its constituent parts, much like the white light from the sun is divided into a rainbow when it passes through a prism, depicted here. Or the same effect can be obtained with a multitude of droplets of water in the atmosphere, which creates the beautifully colored arches in the sky that we call rainbows. The same technique was used by Hubble and Newmason to break up the light from distant galaxies and record the result on photographic plates. The light from a galaxy is a complex mixture of all the light emitted by its constituent stars and hydrogen gas, and also by the various effects which absorb and re-emit the same light, for example by dust grains that are found in the space between stars. The spectrum that reaches the Earth contains fingerprint signatures of all the elements that make up the stars and the gas, and those signatures take the shape and the form of strong emission lines, that's to say strong lines of a certain color, or absorption lines where the light from the broad spectrum of the galaxy is missing. To understand the origin of this fingerprint signature, we need to turn to quantum mechanics. According to quantum mechanics, electrons can only orbit the nucleus of atoms at certain discrete energy levels, which are depicted in this diagram as the discrete orbits going around the nucleus, a little bit like a miniature solar system. The actual picture of what goes on inside the atom from a quantum mechanical perspective is much more complicated than this, and not quite the simplified version that I'm presenting here, but for our purposes this will be sufficient to understand the origin of the spectral signature of atoms. Now, because quantum mechanics dictates that the orbits can only take certain specific discrete distances from the nucleus, and each orbit is associated with an energy level of the electron that's on it, that means that when electrons jump from one orbit to the next, they can only emit or absorb set amounts of energy, which has to be supplied or emitted in the form of light. This means that the jumps of electrons between energy levels is translated into a specific wavelength of light that is peculiar to the particular element that we're talking about. This had been known since 1915, in particular thanks to the work of Vesto Melvin Slipher, who discovered the existence of these spectral signatures in distant galaxies, and also that those spectral signatures had a peculiar characteristic that made them different from anything we find on Earth. Hubble, in fact, observed that the more distant the galaxy was from us, the further towards the red end of the spectrum the fingerprint signatures of its constituent atoms were shifted. In this diagram, the spectrum is represented by the rainbow-colored distribution of colors, and the black lines are the signature lines of the hydrogen atom in the visible part of the spectrum, labeled A, B, and C. If you measure the spectral lines in a lab on Earth, they fall approximately in the locations that I've marked in the top diagram in this picture. But the same hydrogen atom, if found in a distant galaxy, has a signature which is now shifted towards the red end of the spectrum, to the right-hand side of the picture. And indeed, the red part of that signature is shifted so much further to the right that it falls outside the visible part of the spectrum into the infrared part of the spectrum. Hubble discovered not just this redshift, which had been already found by Slipher several years prior, but also the fact that more distant galaxies had a redshift that was more pronounced in proportion to that distance from us. The redshift of light that Hubble discovered and charted out over a number of galaxies was puzzling. Hubble interpreted it as a manifestation of the recession velocity of the galaxy, meaning that the light was redshifted because the galaxy was moving away from us. A similar shift that's called Doppler shift, is familiar to us from everyday experience with sound. The pitch of a moving siren that's moving away from us is shifted towards the bass, corresponding to red for light, while it is shifted to a higher pitch if the police car with the siren is approaching to us, which corresponds to blue for light. But the puzzling part was that nearly all of the galaxies observed by Hubble had their spectrum shifted towards the red end of the spectrum, which meant that they were all, or nearly all, moving away from us. Not only that, there was a trend in the amount of redshift, and hence recession velocity with distance. The bigger the distance, the larger the redshift, the larger the velocity at which galaxies were moving away from us. Hubble drew a line connecting distance to redshift. More distant galaxies were moving away from us at a faster rate. The constant of proportionality between the two is today called the Hubble-Lemaitre constant. Its inverse gives an estimate of the time elapsed since the Big Bang. For the faster the universe is expanding today, the younger its age. This was all unknown to Hubble at the time, and indeed Einstein found it puzzling too. In fact, today the redshift is interpreted not very much as a Doppler shift, not a consequence of the galaxies themselves moving away from us while traveling in space, but rather as a consequence of the stretching of space itself between us and the distant galaxies, a reflection of the expansion of the universe. Hubble was keen to share with Einstein his results about the redshift of galaxies, for these appeared to disprove Einstein's model of a static, unchanging universe, which could not explain those redshifts. Indeed, unbeknown to Hubble at the time, his mysterious redshifts were in perfect accord with the theoretical description of the universe put forward in 1927 by the Belgian priest Georges Lemaitre. Lemaitre had found a solution to Einstein's equations of general relativity that described a cosmos whose size expanded over time, a dynamical universe in stark contrast with Einstein's preferred solution of a static universe unchanging with time. Already in 1927, Lemaitre had predicted the relationship between distance and redshift measured by Hubble in 1929. Lemaitre's discovery, however, went unnoticed, as he published it in an obscure Belgian scientific journal. When later Lemaitre personally handed Einstein a copy of his work at the 1927 Solvay Congress, the German physicist said that the Belgian priest's model was, from a physical point of view, abominable. To understand the significance of this, we must now take a step back and discuss the fundamental concept at the heart of Einstein's equations of general relativity. General relativity is built around a simple principle with far-reaching consequences: that acceleration due to gravity is indistinguishable from acceleration due to motion through space. If you are in a spaceship with no windows and measure a downward acceleration of 9.81 meters per second square, there is no local experiment you can perform inside the spaceship that will tell you whether the spaceship is stationary on the surface of the Earth, like in the right-hand side of this picture, and the acceleration is therefore due to the presence of the Earth mass, or whether it is actually accelerating upwards in empty space under the influence of its rockets at the same rate. This is called the equivalence principle, which Einstein formulated already in 1911 and then used as a guide in his development of general relativity, which he unveiled in 1915. General relativity is a geometric theory of gravitation. At its heart, it says that what we experience as the force of gravity, in Newtonian terms, is in reality a consequence of the shape of space, which is bent by the presence of mass. Einstein's equations of general relativity link together the shape of space-time with the distribution of mass and energy in space. Despite Thomson's misgivings about explaining general relativity to the man in the street, theoretical physicist and creator of the concept of wormhole John Wheeler neatly summarized it in simple terms. Space-time tells matter how to move. Matter tells space-time how to curve. When Einstein attempted to apply his equations to the whole universe, he quickly realized that the presence of mass in the form of galaxies would lead to the universe collapsing onto itself. Einstein's conception of the universe at that time was that of a finite, never-changing sphere containing a homogeneous distribution of matter, at least on sufficiently large scales. In fact, in his 1917 paper where he presented his static cosmology, he offhandedly dispatched comparison with observations by stating, "Whether from the standpoint of present astronomical knowledge my view of the universe is tenable will not here be discussed." This was a theoretical physicist's view of the universe. Because he wanted to have a static universe, he saw it necessary to modify his earlier equations by introducing a new piece, a new universal constant which he denoted with the Greek letter lambda. Einstein used lowercase lambda. Today's usage is to adopt the uppercase letter instead. The presence of lambda described the repulsive force that filled the whole space, which counteracted the attractive force of gravity exactly if lambda was chosen appropriately to match the mean density of the matter filling the cosmos. Einstein fully realized that his new constant complicated the simple beauty of his theory without there being any observational support for its existence. In March 1917, he wrote to the mathematician Felix Klein, "The new version of the theory means, formally, a complication of the foundations, and will probably be looked upon by almost all of our colleagues as an interesting, though mischievous and superfluous stunt, particularly since it is unlikely that empirical support will be obtainable in the foreseeable future." Einstein's conviction of the immutability of the universe was strong enough to force his hand and change his theory to match. When the Russian mathematician Alexander Friedmann first and Georges Lemaitre later came up with alternative solutions that did not require the lambda term, but describe an evolving dynamic universe, Einstein staunchly opposed them. But by 1930, Einstein's conviction began to wobble. The English astrophysicist Arthur Eddington, who had played a major role in publicizing Einstein's theory to the English-speaking world and improving him right with the 1919 solar eclipse expedition, convinced him that his static universe solution was unstable. He also generously acknowledged that Georges Lemaitre had reached this conclusion first when he learned of the priest's work. Eddington, in the same occasion, also apprised Einstein of the latest observational developments, including Hubble's observations. By the time he reached Pasadena, Einstein was ready to pivot. During his visit to Pasadena, Einstein was exceptionally busy. He was being invited to all sorts of functions and all sorts of events, including the premiere of City Lights, and here we see him picture with none other than Charlie Chaplin in Los Angeles. On the scientific side of things, Einstein took part in several meetings with theoretical physicists at Caltech, led by the General Relativity expert Richard Tolman, and the astronomers of Mount Wilson, where Hubble, who was nicknamed the Major, with his imposing figure and impeccably dressed, was keen to be pictured next to the German genius whenever a group photograph was taken. Hubble was towering over him with his 6 feet 2 inches athletic stature. The national press ran a blow-by-blow account of every utterance of Einstein's, who, it was reported on the front page of the New York Times, had come to California to seek the help of the scientists at Mount Wilson Observatory and the California Institute of Technology to solve the major problem of his mind, whether gravitation, light, electricity, and electromagnetism are not different forms of the same thing. The visit came to its climax on February 4, 1931, when Einstein gave a scientific seminar in German in the library of Mount Wilson Observatory. At the end of an hour and a half of highly technical discussions of general relativity equations, when he was asked to explain the relationship between his equation and cosmology, he declared with a quizzical smile that, regardless of what field equations are used, space never can be anything similar to the old symmetrical space theory. An Associated Press reporter, Walter B. Clausen, wrote that Gasps of astonishment swept through the library of Mount Wilson Observatory today, when Einstein, with a few simple words, made the revelation. His old static model of the universe was dead. The report then goes on to attribute the merit for changing the mind of the Berlin professor to, quote, two great California scientists, the astronomer Dr. Edwin P. Hubble of Mount Wilson Observatory and physicist Dr. Richard Tolman of Caltech. The day after, the story made the front page of the New York Times and many other national and local newspapers. The Springfield Daily News, the local paper of Hubble's hometown in Missouri, ran a headline that read, "Youth who left Ozark Mountains to study stars causes Einstein to change his mind." Hubble was catapulted to international fame as the man who proved Einstein wrong. There are, however, reasons to believe that the story didn't quite go this way. It is true that Einstein abandoned his old static model of the universe during his visit to Pasadena. A week later, he emphatically told reporters that, quote, "the redshift of distant nebulae has smashed my old construction like a hammer blow," and even in so doing, he swung down his hand to illustrate the smashing of his model. However, for a man whose work supposedly made such a forceful impression on Einstein, Hubble is given very short shrift in the Berlin professor's personal diary. Not only is Edwin Hubble never mentioned by name in Einstein's diary during his visit to California, he is not even name-checked in the farewell address Einstein gave to the Pasadena community before taking his leave on March 1, 1931. Whether or not Hubble was the instigator of Einstein's conversion to a dynamic universe, one that could do without his troublesome lambda term, we will never know. Perhaps Einstein had already been convinced by the many theoretical criticisms of his static universe model voiced by Eddington, Friedmann, Lemaitre, and de Sitter, a Dutch mathematician and astronomer who had proposed a model of a dynamic universe entirely devoid of matter. Perhaps, for Einstein, the mystery of the observed redshift was merely the last nail in the lambda coffin, not the clinching argument the press made it out to be. It appears, however, that Einstein, the gifted theoretician, did admire Hubble's painstakingly difficult observational work. Upon returning to Pasadena in November 1931, this time never to go back to Hitler's Germany, one afternoon Einstein broke the silence to tell Hubble's wife, Grace, "Your husband's work is beautiful, and he has a beautiful spirit." Upon his return to Europe after his first visit to Pasadena, Einstein wrote a paper in which he made it plain that his old static universe was no longer tenable. Lambda was dead, at least for the man who invented it in the first place. Others felt differently. Without a cosmological constant, the estimated age of the universe was smaller than the age of the solar system, which was an obviously problematic discrepancy that Einstein attributed to the idealized nature of assuming a universe uniformly filled with matter, so very unlikely our own, where millions of light years of emptiness separate galaxies containing hundreds of billions of stars each. Whether or not the intergalactic void is truly empty is a question we shall return to. In 1956, a year after Einstein's death, Russian émigré physicist George Gamow claimed that Einstein described the cosmological constant to him as, quote, "the biggest blunder he made in his entire life." This remark grew to become legendary, and to this date, there is no certainty whether Einstein truly ever put it in these terms. No statement of this kind has ever been found among his numerous papers, although not all of them have been fully scrutinized yet. Also, Gamow's reputation as a man prone to pranks and the occasional hoax, as well as being a heavy drinker, didn't help in establishing the truthfulness of his report. On the other hand, two other physicists, Archibald Wheeler and Ralph Alpher, also claimed to have witnessed Einstein making the remark. Whether he actually described lambda as his greatest blunder or not, there is no doubt that Einstein never regretted jettisoning it from his equations. In a 1947 letter to Lemaitre, he explained that he considered the cosmological constant ugly He wrote, "Since I have introduced this term, I always had a bad conscience. I found it very ugly indeed that the field law of gravitation should be composed of two logically independent terms which are connected by addition. One of the two terms is the part that describes the shape of space, the other term is the lambda term that he added." Einstein went on, "About the justification of such feelings concerning logical simplicity, it is difficult to argue. I cannot help but feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature." In the 4 decades after Einstein's death, his rejected brainchild underwent alternating fortunes, all the while stubbornly refusing to be written off. The working hypothesis for the makeup of the universe became the so-called Einstein de Sitter model, in which the universe contains only matter and no cosmological constant, and the average density of matter is such to make the geometry of the universe and the geometry of space flat. For more details, I've described what that means in my Gresham lecture, Weighing the Universe. In the Einstein de Sitter model, the geometry of space is Euclidean, which means that parallel lines meet at infinity, and the universe's expansion slows down under the influence of gravity, generated, in a Newtonian sense, by the mass contained in the universe. It is a beautifully simple universe, where both spatial curvature and the cosmological constant are slashed away with a fell swoop of Occam's razor, the principle that simpler theories ought to be preferred over more complicated ones if they are sufficiently able to explain the data at hand. At the dawn of observational cosmology, data were preciously scarce, and the Einstein de Sitter model seemed at first an adequate description of the universe. By the early 60s, though, through the works of astronomers Walter Baade and Alan Sandage and others, the rate of expansion of the universe, which Hubble had overestimated to 500 km per second per megaparsec, was revised very substantially downwards. The new estimates went down to about 75 km per second per megaparsec. This, in turn, increased the estimated age of the universe from Hubble's 2 billion years, which was younger than the age of the Earth, approximately 5 billion years, to a much more substantial 13 billion years. But the Einstein de Sitter model soon ran into troubles. Observers consistently failed to find evidence for the necessary amount of matter to make the universe flat, as predicted by the model, a situation that didn't improve even after the introduction of dark matter. Over and over again, observations indicated that the total density of matter in the universe was around 30% of what was required to make the universe flat, as in the Einstein de Sitter model. In this diagram, we see the total matter of the universe represented by the yellow slice, about 30% of the total, but the majority was still missing, despite the fact that inside the yellow slice of the pie, only about a sixth of the matter was in the form of normal atoms, the rest being made up of a newly invented new kind of particles, which we haven't found yet to this date, called dark matter. I talk more about dark matter in my Gresham lecture, Mysteries of the Dark Cosmos. The situation became even more puzzling in the 80s and early 90s, when a new theoretical idea, combined with the first observations of imperfections in the leftover light from the Big Bang, pushed some theorists to turn in desperation towards lambda once again. The theory of inflation was introduced to explain the otherwise incomprehensible observation that the leftover light from the Big Bang, called the cosmic microwave background, has the same average temperature everywhere in the sky, a uniform 2.72 Kelvin, minus 269 degrees centigrade, that has no reason to be, given that patches in the sky that are separated by more than twice the diameter of the full moon would never have been in contact in the Einstein de Sitter model. So if patches of the sky 2 full moons apart have never been in contact between them, what was then responsible for the fact that they had exactly the same temperature? Inflation was the deus ex machina that came to the rescue, by positing a burst of exponential accelerated expansion at the very beginning of the universe, which is depicted here as the line shooting up almost vertically very early on in the history of the universe, which took a very small patch of space and in a very short amount of time enlarged it by over 40 orders of magnitude. With this process, which was powered by an unknown entity which we call a scalar field, we could take a small region of space that was initially all at the same temperature and stretch it out so much that under ordinary non-accelerated expansion conditions, it would appear to have never been in contact. The inflationary model made the forceful prediction that the universe today ought to be spatially flat, exactly like the Einstein de Sitter model, since any initial curvature of space would have been ironed out and flattened out by the exponential accelerated expansion early on. While inflation seemed to support the idea of an Einstein de Sitter universe, in 1992, the first detection of fluctuations in the otherwise uniform temperature of the leftover light from the Big Bang spelled disaster. The amount of fluctuations was as expected in a universe filled with a combination of normal matter and dark matter, but only if the present rate of the expansion of the universe was smaller than 50 km per second per megaparsec, in stark contradiction with Hubble Space Telescope measurements that put it at 80 km per second per megaparsec. The alternative was a flat universe, as supported by inflation, but where the total matter and energy of the cosmos was supplied by a combination of normal matter, dark matter, and a substantial cosmological constant, perhaps as much as 70% of the total. Einstein's superfluous stunt was back on the table. The lambda revival of the early 90s brought to the fore a very different kind of cosmological model than Einstein's original static universe. While in Einstein's proposal lambda was carefully picked to exactly counterbalance the gravity due to matter and so to create a static, if unstable, universe, in this new model, lambda was the predominant player in the contemporary universe. Theorists moved the lambda term from the left-hand side of Einstein's equations, where he had put it, and where it described the curvature of space-time, to the right-hand side, where the matter and energy content of the cosmos reside. This led to a different physical interpretation. Lambda became a new form of energy, filling uniformly the whole of space, and with the uncanny property of possessing negative pressure. The notion of dark energy was born, a reinterpretation of Einstein's lambda term. Dark energy, differently from dark matter and its gravitational attraction, has a repulsive effect on the expansion of the universe, which leads to an accelerated expansion, much in the same way as inflation in the very early universe. The effect of dark energy only comes into play relatively late in the life story of the universe, around 6 billion years ago. This model, depicted by this pie chart here, is today called lambda CDM concordance model, where lambda stands for Einstein's cosmological constant, or dark energy. CDM stands for cold dark matter, a type of dark matter candidate, and concordance expresses the fact that it is in good accord with most cosmological observations. In the lambda CDM model, once the universe emerges out of the accelerated expansion powered by inflation right after the Big Bang, its expansion speed slows down. For the first 50,000 years, the slowing down is caused by radiation, that's to say, light of all types and neutrinos, while for the next 7 billion years, the slowing down is caused by matter, both dark and visible. At this point in time, 6 billion years ago more or less, dark energy becomes important and the expansion speed picks up once again, presumably continuing accelerating into the future for all of eternity. This model of the universe was hotly debated in the early 90s, as it seemed too ugly from a theoretical point of view, requiring as it did not one, but two dark unknown entities, dark matter and dark energy, which together were allegedly responsible for 95% of the contents of the universe. Many cosmologists hang on to the conceptually simpler Einstein de Sitter model, hoping that the missing matter would somehow turn up in the observations. Two teams of astronomers, one led by Adam Rees at Johns Hopkins University and Brian Schmidt at Australian National University, and the other by Saul Perlmutter at the University of California, Berkeley, independently and almost simultaneously set out to measure the deceleration of the universe today. They hoped that by determining precisely by how much the universe's expansion is slowing down today, they could settle once and for all how much matter it contains. But, as Saul Perlmutter would say later when collecting his half of the Nobel Prize for Physics in 2011, well, you can't trust the theorists. They've all been telling us all sorts of things that turned out to be wrong once we actually did the measurement. The astronomers turned to a new tool to try and determine the expansion history of the universe, in an attempt to peer much further into space than Hubble ever could. Their key challenge was to measure the relationship between the redshift of galaxies and their distance from us, much like Hubble had done, but to much bigger distances, up to 8 billion light-years away, compared with Hubble's relatively meager 6 million light-years. Mere galaxies weren't up to this task. What was needed was a much more powerful light beacon, one that could be seen from billions of light-years away and whose power output was known. By measuring the amount of light from the beacon reaching the Earth, the astronomers could estimate its distance, as the light flux is reduced in proportion to the total amount of expansion the universe underwent between the moment when the light was emitted and today. It was extremely important to choose beacons that were both bright and reliably uniform in the amount of light they emitted. This is because if different beacons produce different amount of lights, the measured flux at the location of the Earth would be a reflection not just of their distance from us, but also of their intrinsic variability, which would invalidate distance measurement. The two teams, known as SPC, led by Perlmutter, and HZT, led by Schmidt and Rees, then a postdoctoral researcher, chose as beacons a type of stellar explosions called supernova type 1a. A supernova type 1a, depicted here as the bright dot next to the galaxy, occurs when a type of old, compact, and very dense star called a white dwarf gains mass from a companion star. White dwarfs pack the mass of the Sun into a cold star the size of the Earth, with the result that one spoonful of white dwarf matter weighs about a ton. If a white dwarf is in a binary orbit with another star, depicted here on the left, a regular star, or another white dwarf, like in the right-hand side diagram, it can gain additional mass by sucking in gravitationally the gas from the companion, if it's a regular star, or by merging over time with a second white dwarf, with the orbits declining because of the emission of energy in the form of gravitational waves. The resulting additional pressure brought about by the additional matter onto the core of the white dwarf sets off a runaway thermonuclear chain reaction that in a fraction of a second completely destroys the star, emitting an enormous amount of energy, about 10 billion times the yearly power output of the Sun. The bright phase of the supernova lasts for about 3 weeks, after which it fades away and becomes undetectable a year or so after the explosion. The famous new star which appeared in Cassiopeia and which for a week in November 1572 shone more brightly than Venus was a supernova type 1a exploding in our own galaxy, the Milky Way. It is now called Tycho supernova, as it was observed and described in great detail by the greatest naked eye astronomer of all times, Tycho Brahe. Supernova type 1a, bright as they are however not all exactly the same. The amount of light they emit in the explosion depends on the details of how they gain mass and how the thermonuclear reaction unfolds. Also, their light is dimmed and reddened by interstellar dust it encounters on its way to us, both in their host galaxy and in the Milky Way. The SCP and HZT teams went to great length to correct for all of these important effects, and once their independent analysis of 42 and 10, respectively, new very distant supernovae were concluded, the result was astounding. The universe was not decelerating as in the Einstein de Sitter model, but it was clearly accelerating in its expansion as predicted by the lambda CDM model with 70% of dark energy. Brian Schmidt, who shared a quarter of the Nobel Prize for the discovery, expressed the sense of surprise and self-doubt that overcame both teams at that time. He said, what we were trying to prove was the universe slowing down a little or was it slowing down a lot? So when the result came about, I just said, all right, why did we mess up? But they hadn't messed up. The fact that two independent teams arrived at the same conclusion using different data and different analysis methods was seen as a powerful indication that the result was correct, unexpected and mysterious as it was. Despite numerous challenges, both from the observational and data analysis perspective and from the theoretical point of view, the result of an accelerating lambda-dominated universe stands. The original supernova collection has been now increased to well over 1,000 supernovae type 1a, and we will soon be able to observe tens of thousands of supernova explosions per year. We can see in this diagram the compilation of the original data that led to the discovery, and you can see in the bottom part of the plot the difference between the various kinds of universes we have considered. The top line, the top solid line, is the concordance model, the lambda CDM model with 30% matter, 70% dark energy. The middle horizontal dotted line is a model with the same amount of matter but no dark energy. And the bottom downwards curving line is the Einstein de Sitter universe. They are not very different, those three curves, and yet we can see the bunch of points lying clearly above the horizontal zero line in this plot. Those are the high distance, high redshift supernovae discovered by the two teams, which together lift up the value of those lines and demonstrate that the Einstein de Sitter model, the downward curving line, is untenable, and in fact the lambda CDM concordance model, a flat model with 70% dark energy, is the best explanation for the observations. The second plot shows a modern version of this diagram with many more supernovae collected in the meantime, and again we can see that the matter-only Einstein de Sitter model, the blue downward curving line, is very much in disagreement with the red cloud of observations of supernovae that singles out a lambda CDM universe as the best model describing the expansion history of the universe in the last 6 billion years or so. The universe appears to be accelerating in its expansion, powered, we think, by the mysterious, mischievous stunt of Einstein's that turned out not to be superfluous after all. Einstein's blunder has turned out to be a prescient idea, put forward for the wrong reason ahead of its time. Dark energy is today one of the greatest mysteries of physics. Some physicists believe it is just the tip of the iceberg of a much deeper revolution awaiting to be uncovered. For it has become clear since Einstein's time that if dark energy is just another constant of nature, like Newton's constant, setting the strength of gravity, or the charge of the electron setting the strength of electromagnetism, then the smallness of its observed value cries out for an explanation. It is true that dark energy makes up 70%, the majority of the contents of the universe today. However, from a particle physics perspective, its energy is ridiculously small. It accounts for 70% of the total only in virtue of another peculiar and uncanny property. As the universe expands and its volume grows, the density of matter decreases in inverse proportion to the volume, while the density of dark energy remains constant. This could be a reflection of dark energy being a property of empty space itself, what physicists call the vacuum. The vacuum of particle physics is nothing like the boring emptiness one would naively imagine. On the contrary, according to quantum mechanics, it teems with a soup of virtual particles, emitted and reabsorbed all the time, all too quickly for them to leave any observable trace. Except perhaps for a ghostly zero-point energy, the energy of the vacuum itself. This is usually unobservable, but in cosmology it may manifest itself precisely as dark energy. The trouble with this explanation is that the quantum mechanical calculation of this zero-point energy fails spectacularly. We know that at some point our quantum mechanical theory of the infinitesimally small breaks down. As we look at particles with higher and higher energies, we reach a point beyond which the standard model of particle physics loses its validity, as it is unable to incorporate gravity. Depending on what one assumes about the maximum range of validity of the standard model, the prediction from quantum mechanics for the zero-point energy of the vacuum differs. Even if we imagine that our current theories of the quantum world cease to work just above the energy range currently explored by particle physics colliders, such as the Large Hadron Collider, at which scale our quantum mechanical theories work perfectly, the predicted zero-point energy is 40 orders of magnitude larger than what would be required to explain dark energy as vacuum energy. In other words, the quantum mechanical prediction is vastly bigger than what you need to be able to use it to explain the dark energy as observed in cosmology by the accelerated expansion measured with the supernovae. If dark energy is indeed a manifestation of the energy of the vacuum, nobody has been able to show why it should be so small. Except perhaps by turning the problem on its head. Nobel laureate Steven Weinberg, who played a major role in establishing both the model of fundamental interactions and the concordance model of cosmology, frustrated with the fruitless attempts to explain the smallness of lambda, speculated in 1987 that, quote, perhaps lambda must be small enough to allow the universe to evolve to its present nearly empty and flat state, because otherwise there would be no scientists to worry about it. If we are to exist, Weinberg went on, the cosmological constant cannot be too large, as predicted by quantum mechanics, or its repulsive effect early on in the expansion of the universe would prevent the formation of galaxies and stars, and hence the evolution of biological beings, such as ourselves, able to measure it. Once galaxies are formed, the cosmological constant can continue to expand them away from each other without further influencing the processes leading to sentient life. The production of heavy elements in stars, the formation of planetary systems, the synthesis of organic molecules, the assembly of primitive life forms, and the relentless trial and error of evolution. They can all safely proceed in the cocoon of the gravitational potential of a galaxy, such as the Milky Way, oblivious to the constantly increasing redshifts of other galaxies, millions or billions of light years away. Weinberg's original study predated the discovery of dark energy by over a decade, and he concluded then that this kind of argument failed to explain the smallness of lambda. Indeed, Weinberg's requirement that lambda be sufficiently small for galaxies to form before the universe begins accelerating leaves the possibility open that lambda could be hundreds of times larger than it is in our universe, something that was observationally ruled out already at the time of Weinberg's paper. However, the core idea that the existence of complex biological forms such as ourselves might say something about the likely value of lambda in our universe, this is now called the anthropic cosmological principle, has been investigated in much further detail. The central requirement is that there exists not only one universe, but a multitude of universes, all with different values of lambda, and possibly of other laws of nature as well, varying across this unimaginably complex landscape of universes, which is called the multiverse. Across such a vast multiverse, life would sprout and flourish only in the minority of universes, the corners where lambda is sufficiently small for galaxies to exist in the first place, our universe among them. The question then becomes, what creates this plethora of universes? One elegant possibility is to hark back to inflation. Maybe our universe is only one patch of a collection of universes, all being inflated in different ways and each with its own physical properties, among them lambda. Such a scenario is not directly testable, for we have no access to these other corners of the multiverse. But as we learn more about the properties of inflation, we may be able to better understand whether this is an actual possibility. In 1917, at the time when the Milky Way was thought to be the only galaxy in the universe. Einstein wrote to De Sitter with remarkable farsightedness. He said, quote, "One day, our actual knowledge of the composition of the fixed star sky, the apparent motions of fixed stars, and the position of spectral lines as a function of distance will probably have come far enough for us to be able to decide empirically the question of whether or not lambda vanishes." Not even Einstein could, however, have predicted that the discovery of a non-vanishing lambda would push his successors to multiply universes ad infinitum, in the desperate hope of finally explaining the origin of his mischievous stunt. I am sure, however, that Einstein would have reveled in the grand vistas on the nature of the universe that were revealed to us by his greatest blunder.